We're going to be looking now at graphing exponential functions. We're going to compare this first to something that we know really well, and that's linear functions. So a linear function is a constant rate of change, which makes it a straight line. This is like Benita in the AV and the Benita problem, where their pay was going up by $100 every week. So it's a constant rise over run. Okay, so in our example, it's up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. The change is constant. That's what creates a straight line. Exponential, however, is not a constant rate of change. It increases rapidly. This is like AV, who started off only paying a penny, then 2 pennies, and 4 pennies, and 8 pennies, and kept doubling and doubling and doubling. It creates a curve in our graph. So AV's pay started off really small, but then as the days went on, it increased substantially. That rapid increase causes a curve in the graph, and that's what makes it an exponential function. If we look at this in terms of a table, when we were looking at linear functions, we wanted it to increase or decrease by the same amount. So my change in x is a constant rate of plus 1. My change in y is a constant rate of minus 2. That's what makes it a linear function, is that it's going up or down, adding or subtracting by the same exact amount. The difference with exponential functions is that our y values increase more rapidly in this case, or sometimes it can decrease, but it's a multiplier or divider. So between every single y value or every single output, it is a change of a multiplier of 2. If we look at it in the reverse, we're dividing by 2. So exponential functions, when we're looking at tables, has a multiplier rather than addition and subtraction like in linear functions. The last difference we're going to look at is the equation. So we use the equation slope-intercept form y equals mx plus b time and time again to determine if it was a linear function or not. And the important part is that it had an exponent of 1. Well, the equation that we're going to look at for exponential functions is y equals a times b to the x power. Notice that our exponent is where the x is. That's what makes it an exponential function. So how are we going to graph these? So I'm looking at the exponential function 2 times 2 to the x power. I'm going to substitute in the values -2, -1, 0, 1, 2. So when I start with -2, I have 2 times 2 to the -2nd power. Remember, a negative exponent does not mean it's going to be a negative number. It means it's going to be a fraction. So I could rewrite this as 2 times 1 over 2 squared, making my negative exponent positive. So I have 2 times 1/4, which is a half. Then I plug in -1. So 2 times 2 to the -1st. 2 to the -1st power is a half, and 2 times a half is 1. I plug in 0. 2 times 2 to the 0 power. Anything to the 0 power is 1. 2 times 1 is 2. Since I know that my pattern is a multiplier, I can look to see and evaluate my table. So a half times 2 gives me 1. 1 times 2 gives me 2. So if I continue that pattern of times 2, my next value would be 4, followed by 8. And then I'm just going to plot those coordinates. So I have -2 and 1/2, -1, 1, 0, 2, 1, 4, 2, 8, and that creates my exponential function. So I can make subtle changes to my exponential function, all right, by adding values on to my x or adding values on to the end of the function. So if I take x and I subtract 4 from it, we worked with this a little bit with absolute value. When I subtract 4 from it, that moves our exponential function in the horizontal manner. So when I subtract 4, it moves me 4 spaces to the right. Whatever I add or subtract is my vertical shift. So adding 3 moves me 3 spaces up. So I can transform this function by moving my original function 4 spaces to the right and 3 units up. So 4 spaces to the right, 1, 2, 3, 4, 3 units up. 4 to the right, 3 up. 4 to the right, 3 up. So I have the same exact graph, but it is a horizontal shift to the right and a vertical shift up. We're going to graph one more time just to make sure we have it. This time I'm looking at a factor of 1/2. So this is really 1 times 1/2 to the x power. So if I take 1/2 to the negative second power, I have to take the reciprocal to make it a positive exponent. So that's really saying 2 to the second power, which is 4. Evaluating 1/2 to the negative first power. So once again, I take the reciprocal to make it a positive exponent. 2 to the first power is 2. 1/2 to the 0 power. Anything to the 0 power is 1. And I can look to see the pattern that I'm starting to form. From 4 to 2 is multiplying by half or dividing by 2 each time. So 1 divided by 2 is a half divided by 2 is a fourth, and now I can graph my exponential function. So I'm at -2, +4, -1, +2, 0, 1, 1, 1/2, 2, 1/4. Okay, notice that when I have a factor that is a fraction between 0 and 1, it actually turns our exponential function to the other side. So we're actually decreasing. This is different than our function before, where I had a function that was greater than 1, and it was an increasing function. So what is that going to look like if I make a few changes? So now I have a multiplier of negative. That's going to flip your exponential function upside down. It actually reflects over the x-axis. The +2 is 2 to the left, and -5 is 5 down. So I'm going to flip my +4 1 down, and then I'm going to go 2 units to the left, 1, 2, and another 5 down, 1, 2, 3, 4, 5. I'm going to continue. I'm going to flip my 2 across the x-axis. I'm going to go 2 to the left and 5 down. Flip my 1 across the x-axis, 2 to the left, 5 down. My 1/2 across, 2 to the left, 5 down. to get my new exponential function. So our graph y equals a times b to the x is our exponential function. The a value is our initial amount, and it's actually going to be the y-intercept. If we look back at our two graphs, I had an a value of 2, and we crossed at 2. I had an a value of 1, we crossed at 1. The b is our scale factor, so what the multiplier is for each table. So if I look back, I had my scale factor was 2, and that's what my multiplier was, times 2 times 2 each time with my output. I had a scale factor of 1/2. That's what my multiplier was, times half between each output. And then to the x power is our exponent.